Okay, so we've been doing a series of papers on distillation. This is the third paper, already. Yeah, it's back here. We've been doing, so this is the third paper on distillation. Distillation is a very simple mechanism, training mechanism for transfer learning, but which apparently has very interesting properties. So the one that we're going to be talking about today is how to protect a deep neural network against adversarial attacks. There are a few caveats in the paper, but just as a preview, I think that one of the main things of this paper is that it explains in a lot of detail what the first paper that we presented did not explain. And the first paper was the one that introduced distillation to the world, so to speak. This paper actually goes into some mathematical trouble to explain why distillation works. And I think that's one of the strong points of the paper. And as a second strong point, it seems that it solves one type of adversarial attack. So let's start very quickly by describing what an adversarial attack is. And it's actually very simple. It's when you have a trained model, you deploy it in a sensitive setup. You might have people trying to break your model. So for instance, if we have a classification model, and this model is deployed in self-driving cars and the model is trying to detect other cars, an adversarial attack might be a corruption of the input data such that the car is now no longer classified as a car, but it's classified as a cat. So that, of course, is a problem with the collision detection software, and it is something that we want to avoid at all costs. Another example can be in spam detection. So if you want to filter spam emails and your system is trained to classify between spam and not spam, an adversarial attacker will try to tweak their text a little bit so that your classification network classifies it as not spam, and then the user receives it. Another example, medical images. If you're trying to classify between a tumor, for example, and non-tumor, same thing. If you tamper with the image a little bit, maybe your classification system will have a decreased accuracy in the detection of the tumor. Now, there are a few things that need to happen for the adversarial attack, but the main one is that the adversarial image has to look a lot like the original image. Why? Because if a human can easily detect the adversarial attack, then the attack is very likely going to fail. So that is the main thing about adversarial attacks. They look very similar to the original image, but they cause them. Maybe I should make this a bit bigger. Okay. So that's a cipher 10 image. So it looks very close to the original image. A human can still classify it as the original image, but then our network classifies the car as a cat. So yeah, I'm gonna need that.
Ah, okay.
No, don't worry. So it's classified as a cat. Okay. Just to put the notation in context for the paper, let's assume that we have an input example x, which can be whatever. This is going to go through a deep neural network. Let's call that set of x. And just for the sake of argument, this set of x is going to produce the logits, so the outputs that go into the softmax output. Okay, so this is going to produce our set I of x, and then we're going to have a function f of set, which is going to be our softmax activation. Okay, and this is the one that's going to produce our classification output. Let's call it y. So formally speaking, an adversarial attack is a change to x, let's call it delta x. Let's call it delta x, such that, let's call x asterisk is your adversarial sample called x plus delta x, such that f of x asterisk equal y asterisk is not y the correct output. Okay? And that is the most basic definition of the adversarial attack. And one thing to bear in mind is that if the attacker has access to the weight, the adversarial attack becomes trivial. So you can very easily find gradients and find ways to craft the adversarial attack. So that is a bit obvious. That is the main focus of the paper is, let's say the attacker has access to weights. How do we protect against that? But it has also been shown that even if the attacker does not have access to the weights, but is able to replicate the function closely enough, so if they make a surrogate function for this f of z, and they craft their adversarial attacks with that surrogate function, those adversarial attacks also translate to the original model. So for the sake, so it is worse if they have the weights, but if they don't have the weights, the adversarial attack still works. So that is a bit what this paper is trying to tackle. Cool. So let's get a bit of insight on how to craft these adversarial attacks. Of course, they can be very different. How to make adversarial samples has many different outcomes. This paper focuses on a particular one, which is called the source target misclassification, which means that if you have an input and a target and a correct output, you can craft your adversarial attack such that y asterisk is whatever class you want it to be. Okay, does that make sense? So this delta x has to be small with respect to a norm, and then you can make y asterisk be whatever class you want it to be. So an example in the so in mlist, that's 0. If you want it to be 5, you introduce a few points here and there, and you make the classifier classified as 5. 3 can make it classified as 8. This one you can even see where the adversarial samples have been tampered with, and so on. Okay, and same here. You can put a few samples here and there, and then you can make the boat look like an airplane. Okay, so that's what we call the source target attack. Cool. So how are these? So to understand why distillation, or why what they call defensive distillation works, it helps a little bit to understand how these adversarial samples are crafted. And we say crafted because it's almost an art to make the samples. They're not made manually. They are of course made with an automatic method, which is broadly divided into two parts. The first part is what they call the direction sensitivity estimation, and the second part is the perturbation selection. So what we're trying to look for, so the objective of this is to find the optimum for this cost function. So you want the argument that minimizes delta x. So you want the argument that gives you the minimum delta x for a given norm that you can define whatever that norm is, depending on what type of attack you want to be, such that such that f of x plus delta x equals y asterisk, where y asterisk is whatever you want. So for instance, if you make this be an Euclidean distance, that means that it's going to make a perturbation on all the features, but they're going to be as small as possible, so that the adversarial attack looks as close to the first image, but perturbing all the features. So you would imagine making like so if you have a 2x2 image, you're perturbing, for example, the shading of the image. So they are all perturbed. If you make a distance matrix based on saliency maps, then you're going to be looking to perturb as least features as possible, also with a very